Only probably could have just like could have probably just like started with that.
Last call for homeworks. Well, good afternoon, folks. Welcome back to another Chem 400 lecture. The number of Chem 400 lectures is rapidly dwindling. We are approaching the end of the semester. As I'm sure you know, we do have a third midterm exam. Why do we call it a midterm? I should just call it an exam because it is at the very last day of lecture. One other announcement. I will not be here December 4th. That's a Wednesday. I have found a sub for the lab practical, and I will keep you up to date whether we will have lecture and or discussion that week. As far as I know, it is unclear. Let's see, what else? Lab 9 next week, and then the lab practical the week after Thanksgiving. Question, Maddie?
So you're not going to be here for the lab practical?
I'm not going to be here for one day of the lab practical. True. For you, in fact, for all the Wednesday morning people. So, but I have a very qualified sub who will be as tasky, if not more, than I am about making sure it runs efficiently. Other questions? Yes, Leo?
So on the day of the lab practical, we don't have a lecture.
So what I'm saying right now is you definitely have the lab practical. You may have lecture. I just found out about December 4th, and my first thing was to make sure that everybody had a lab practical that week. So, but yes, you may have lecture and you may have discussion, those of you who have discussion. Yes, any other questions? So, stay tuned, as they used to say when people tuned in to watch things like television to actual channels. Now, where were we as far as lecture goes? As I mentioned before, earlier, so I am subbing for another instructor, so I am doing chapter 10 twice, and so I forgot where we were. Everybody helped me get here. I think we're a little ahead of where they were, so I think everything will be fine. But if I start saying the same thing too many times in a row, at least check in with me to see if I mean to be doing it. So I did bring a model of tetrahedral today. We can see that there are 3 of them definitely angled down and in different directions. If we look at the plane of the surface here, then 2 of them are in the plane of the surface. This one comes out at you, this one goes back. And I'll ask again, how many ways are there to correctly draw tetrahedral shape in this class? There's just one, thank you. Yes, and that is the orientation that we're going to do. All right, so now what's new perhaps for Chem 400 over Chem 300 is now we have 5 and 6 electron groups. 5 electron groups around the central atom. The electron geometry is trigonal bipyramidal. The bond angle, well, that's a mistake because there are bond angles. Bond angles 90 and 120 degrees, and I'll show you that in a minute. Hybridization, well, 5 electron groups, 5 hybridized orbitals, s, p3, d. And this kind of hybridization where you have 5 electron groups is going to be reserved for atoms that can have expanded octets, although not exclusively. Here's an example, PF5. Lewis structure for this. Well, the Lewis structure, remember, does not have to show shape at all. It just has to show all the bonds and all the pairs of electrons. And so when you put in all of the fluorines in this case, you can put them anywhere. You can show shape with Lewis structures, but you don't have to. So I just I usually put the 4 that I know, like at north, south, east, west, and then put the 5th one there. And then when I do the shape somewhere probably over here, I'll make sure that my bond angles are correct and things like that. Anyway. Okay, so there we go. Each of the fluorines has an octet. Fluorine, one of those atoms that cannot have an expanded octet, is true. Phosphorus, we said aluminum, silicon, phosphorus, sulfur, chlorine, argon, and the ones below that can have expanded octets if it minimizes the formal charge. Formal charge on this phosphorus, does anybody know what it is? It is 0. 5 valence electrons from the periodic table, 5 bonds. That equals 5 minus 5 is 0. So not surprising. If you had to guess, most atoms want to have 0 formal charge. So guess 0, although of course on your exam you can expect some non-zero formal charges. Any questions about this Lewis structure? Yes, Alicia.
Is it mostly fluorine or phosphorus? The extended octet group has to do more with fluorine or phosphorus? Because you have SF5, you have EF5, I think.
Yeah, fluorine is just a nice thing to bond to it. I don't know, like, we don't talk much about this, though it's not a secret. Fluorine, because it has 7 valence electrons, and because it cannot have an expanded octet, it almost always forms 1 bond. So we're just looking for things that have 1 bond here. Yeah, but phosphorus, so the central atoms are the ones that you have to worry about having expanded octets. Phosphorus atom. So the way this works is you do the electron configuration for the atom. I'm going to do neon, 3s2, 3p3. I will now draw the orbital energy diagram. Oh, I'm going to do neon. Fair enough, those are all core electrons, and so they will not participate in the bonding. I think in the previous ones I did do the 1s. Whoa, my boxes are getting too big. They're heading over into my hybridized atom there, but something like that. From last time, I'm not worried about the spacing between these. You can stack them up like this. You can do them to the side however you want. Now, as far as electrons, I have 2 electrons here. I have 3 electrons in the P. We can see that phosphorus has 5 bonds. It has 5 hybridized orbitals. I'm now going to circle 5 orbitals with 5 electrons. It's actually only one way to do it, I guess. I mean, technically you could circle any of the Ds because all of the Ds are empty. These are going to be my hybridized orbitals. You can see one's an S, one's a D, and 3 of them are Ps. So you can more or less put them at the same energy level as the Ps. There's the boxes. Now let me put in my electrons. Oh, what? I'm sorry. I screwed that one up, didn't I? 3s is gone. 3s has been hybridized. It's one of these 5 now. And all 5 of those electrons are in the sp3d orbitals. Any questions about this? Now let me draw the shape. I said there are 90 and 120 degree bond angles. I brought a model of this one as well. Let me create it for you here. When there are 2 different bond angles, there are 2 different positions, and we will talk about this as well. So this bond angle, what is that bond angle?
90.
That's a 90. What about that one? There's the 120. What we're going to have here is we're going to have 3 positions that are equivalent and then 2 other ones that are different. Let me draw that picture and then I'll describe it for you. I guess I'm going to draw it right here. I'll draw them in different colors. Like so. Bond angle here, 90 degrees. Because they're in the plane right here and one of them sticking out and one of them sticking back, it is tough to see the 120 degree bond angle, but all of these red fluorines have bond angles of 120 degrees. Then anything down to the bottom fluorine has bond angle of 90 degrees. Now I'm going to draw a dashed line there. This is what's going to be generally called these fluorines, these 3 of them are called the equatorial positions, or in this case, equatorial fluorines. They're on the equator of the molecule, if you will. The top and bottom are called axial positions. And what I'd like to do is, since I'm sort of out of space over here, I do want to do another example in addition to the 2 I've got on this page. Shoot, I skipped this page, didn't I? All right, can we go back to that one now? My apologies. All right. And we can still do at least one of these examples. But now let me talk some more about this one, or at least 5 electron groups. The example I'd like to do now SF4. Six valence electrons for sulfur, 4 times 7 for the 4 fluorines, that's 28 plus 6, that's 34 electrons. If I do the Lewis structure, everything comes back to Lewis structures. I attach my 4 fluorines. I sprinkle my pairs of electrons around the fluorines until they each have octets. So far, so good. I'm counting up to 34 as I go. This will be important for this one. So let's see. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. And maybe you knew there was going to be 32 because there's 4 sets of 8 for each of the fluorines. But I still have 2 more electrons to go. Those 2 electrons, doesn't matter where you put them, around the central atom, but they're going to be somewhere around that central atom because fluorine cannot have an expanded octet. Sulfur can. Look at the formal charge on that sulfur. What is the formal charge on that sulfur? Sorry? 0. It is 0. We have 6 valence electrons from the periodic table. 1, 2, 3, 4 bonds. 5, 6 for the extra electrons. That is 0. We know it has to be 0 because there's no charge on the overall molecule and there's no other formal charges. That's one of our checks as well. Plus, we like to guess 0 for these. Now, the reason I want to do this example is because we have a pair of electrons, and I wanted to make the point that if you have a pair of electrons, it always goes to the equatorial position first. Or so, and in fact, if we have up to 3 pairs of electrons, they all go to the equatorial positions. So the statement I'd like to make is, lone pairs of electrons on the central atom go to equatorial positions. Because equatorial positions are slightly farther away from all the other positions than the axial. So because equatorial positions are farther away from its neighbors than axial positions. From neighbors. Let me be from neighboring fluorines in this case. So what does that mean when I draw this picture? So I'm going to essentially draw the same picture as I have here, except that instead of P, I'm going to put an S. And in one of these positions, it doesn't matter which one, I'm going to choose this one. I'm going to put the pair of electrons. So I drew my 5 positions. I've placed my 4 fluorines. Now, here is one thing where there's 2 different options for how you put it. Technically, I'm showing a bond here, which means that really I should do this to put the electrons in the equatorial position. I don't know, I'm okay if you do it like this as well. I can see how this is a little more confusing to some people, and so, again, I don't care how you do it. But whenever you draw this for me, or a similar compound, make sure that the pair of electrons, maybe that's the best one, put them right there like that. And if it's unclear from your drawing whether it's in an equatorial or an axial position, point to the electrons and say equatorial. Although from your drawing, hopefully. Questions about where electron pairs go in these cases? If I had a second electron pair, they could go in either of these positions. A third electron pair would go in the other one. Leo?
So does that mean the equatorial part of all of the shapes is decided by the ones that are farthest away from each other?
So well, let me say a couple more words about this. So the next thing I want to say is that compared to bonds, a pair of electrons is considered slightly more negative charge, and so it is able to get into the position that is farthest away. And in fact, beyond that, they will push the other atoms even farther, meaning if this bond angle is greater than 90 degrees now, that means this bond angle is less than 90 degrees. So electron pairs, and that's why we're going to do at least one, if not both, of these examples, because they have electron pairs as well. These bond angles are going to be less than 90 degrees because the pair of electrons pushes the atoms away. Pushes bonds away. This fluorine, sulfur, fluorine will be less than 120. So I don't know, Leo, if that addresses your question. If not, I'm happy to have you restate or ask again.
Okay, so I guess it's not arbitrary, like what is the equatorial plane of a molecule, right? It's decided by the largest.
So if your question is, how do we decide which is the equatorial plane? It is the plane that has the